And the next talk will be given by Professor Krivtsov from St. Petersburg Polytechnical University, a corresponding member of Russian Academy of Sciences. And the title of his talk is Hooke's Chain. Please, Professor Krivtsov.
Thank you very much, Vitaly. I will switch on the screen demonstration. The title of my talk is Hooke's Chain. What I actually would like to speak about is, I think, the simplest problem in the simplest system considering lattice structures. But still, as I think it's really the complexity of this system is underestimated. And also, as we have our conference is school conference, I think this is my talk is half scientific, half educational, so it has some things which I believe would be interesting to young scientists who attend the conference. And also, I would like to show that this simple system can give problems which are really very complicated, and probably some of them where I don't know the answers. And our colleagues, Antonio Politi and Oleg Endelman, who are here, also I'm very interested in your opinion about what I would like to tell now. Okay, so here we can see on this picture, and I hope, unfortunately, the animation, as I see, probably is not very good translated to the net, but anyway, in the upper row, you can see the simplest oscillator with 1 degree of freedom, harmonic oscillator. And in the bottom, you can see the system with many degrees of freedom, but which contains these simplest oscillators. So I think about the simple oscillator, we know almost everything. But about these systems with high degrees of freedom, even the simplest system, there exist a lot of questions which maybe there is answers to these questions somewhere in literature. But up to my mind, it's very difficult to find it at some certain place. Maybe my colleagues will correct me, but this is what I can see. So I will, let's go to the simplest system, the one-dimensional oscillator. And here you can see what is here actually. Two laws, Newton's law and Hooke's law, which are on the base of which we can obtain the simplest equation of motion of harmonic oscillator. And these two great scientists who actually are named here, Isaac Newton and Robert Hooke, they was not big friends during their life. They live in almost the same time, but they have arguments. Moreover, we don't know how Robert Hooke looked like, so there is no portraits of him, and it's kind of general belief that all his portraits were destroyed by the directives of Isaac Newton. Maybe this is not truly correct, but probably from some point this can be a kind of truth in this information. Anyway, so here you can see on the next picture, this is a kind of imagination of how Robert Hooke can look like. Anyway, the names of these two great scientists give us what we have, the oscillator and the equation, which I think in the basis of the almost all theories, not only physics, but in many other areas of physics. Now, when we combine these elementary oscillators in a chain, which is the simplest chain of equal particles with connected with equal springs, this is, I believe, the simplest system, many-dimensional system. It still doesn't have any certain name. so my suggestion is to call it Hooke's chain, because the main thing is the Hooke law, which is connect the springs. And this could be a short name, and also as a tribute to Robert Hooke, who had done a lot in the foundation of science. Okay, so what we will consider? We will consider, as I say, Hooke's chain in two instances: one infinite, another one periodic. And so because it is not every time easy to explain what is infinite chain, but it can be considered as limit of periodic chain for the high number of particles. Now, the equation for this system is written here. So the coordinates of particles are connected with each other by this differential difference equation. And if we consider displacements or velocities, for them also we have the same equation. And the only parameter is the elementary frequency, which is combined from stiffness and the mass of the particle. Actually, there are many works devoted to this system, partially or fully, but I would like to mention these two works, which are done by great scientists. Both of them are Nobel Prize winners, but both of these works are almost unknown by broad scientific society. One is written in German, another in French, and as far as I know, there is no translation of them to other languages, to English, to Russian, and so on. But this is kind of fundamental. Also, my colleagues, please correct me if you know this kind of translations. It's interesting for me. The first work is written by Erwin Schrödinger in 1914, very long ago. And there is given a general solution of the dynamics of such chain in the terms of Bessel functions, which is called actually the Schrödinger solution. Another work is work by two authors. One of them is Ilya Prigozhin, also the Nobel Prize winner. And here the statistical mechanical aspects of this system is considered. Going to the first work, we can, what was done by Schrödinger? He introduced these two variables, actually one variable, y, which is combined of velocities and displacements. And it appears that the solution of this problem became astonishingly simple. Just this sum of Bessel functions where coefficients are the initial conditions for the chain. This solution can be effectively used to analyze what is happening. For example, let's go, if we consider that all initial conditions except one are zeros, then we will have a so-called fundamental solution. The equation is written here. And the result is, you can see here, which is actually just the Bessel function with even indexes. Where they show something like traveling wave from the point where the chain is excited in the center, and then this wave go to right and to the left. The first question, which is actually quite challenging, if we would like to understand what is happening in between these points. Of course, the solution is defined for integer, only for integer values. But the Bessel function, we know it is valid for any values of indexes. What we will have if we write this graph for real indexes? It's strange, but we see that the result is gives the incorrect representation. At least it does not have the symmetry of the problem, because the problem should be even. It should be the same from the left-hand side and the right-hand side from the point of excitation. So, well, this could be, we can try, there exist different continuum representation, quasi-continuum, I would say, representations, which give the same values in the integer points. For example, the Anger function, which is close to Bessel function, and usually the Anger function is used to calculate Bessels for integer points because it's a much simpler integral. But still we have non-symmetric behavior. The symmetric behavior we can obtain if we solve the fundamental problem using discrete Fourier transform. We'll have some kind of integral representation which is different from representation of Bessel and Anger function, and it will give really the symmetric system, but strangely it is not so regular if we look at amplitude. I will show you again the amplitude of Bessel function, at least for positive values that have very regular behavior. Here it's more complex, and also we can the question is which is closer to kind of reality which can help us to imagine what is happening, because what is happening in discrete system is very difficult. You see, you can see something like chaos there. But in this picture, which is video, and probably hopefully it can be seen a little bit, it is the idea of decomposition of this solution in two waves. The idea is can be found in the book by Professor Kunin, also which was written in 1975. Originally, the idea was that the initial perturbation is decomposed in two packets moving in two different directions. And these packets actually have very amazing properties. For example, the kinetic energy of each packet is constant, not only total energy, but kinetic is constant, potential is constant. They are exactly the half of the full energy. But the sum of these packets, which is the fundamental solution, it does not have constant kinetic energy, it oscillates. And also, as you see, if both packets behave almost quasi-stationary, the behavior of the fundamental solution is much more complex. But anyway, the shape of the packets show us that probably the fundamental solution in this form, in the form of which we obtain from discrete Fourier transform, is more close to the probably rational description of what is happening in the crystal. Again, what is also very interesting that if we consider not the point excitation, but three-point strike, then we have much more regular solution. And here we have this, we can see this decomposition in packets very well, just without the real decomposition in these two parts. Okay, now this is some questions which arise when you consider just simplest behavior of the dynamic behavior of the chain. Much more complex behavior is stochastic behavior, when we would like to describe temperature and things connected with thermal behavior. How this can be done? The idea is to consider stochastic system, and I think probably the first description of this kind was done by Klein and Prigozhin in the mentioned paper. And one of the possible initial conditions can be a heating part, which is written here, where initial displacements are zero and velocities are random functions, which have some kind of profile in the space direction. Also, we can consider more complex situations when we have heat supplies, a winner process, and so on. The main thing is temperature. The kinetic temperature can be described as average over kinetic energy. Not really average if we go in terms of stochastic processes, better considered like a mathematical expectation. In real experiments, we can calculate averaging over a lot of realizations of some system, which we can see here on the picture. And then if we calculate the average or the mathematical expectation, what is important in this case, we can find temperature kinetic. Once more, I repeat, the kinetic temperature in the certain point of system in the certain moment of time, which is very important. Now, the solution of kinetic temperature can be obtained by different ways. By in the paper by Prigozhin, it was obtained again in the terms of Bessel functions. And you can see this formula, which is very close to the formula which was obtained by Klein for the displacements or velocities. Here is the formula for temperature. Actually, it can be obtained for kinetic energies, and for temperature we have exactly the same behavior. And this is very useful and probably not very well known formula. And one of the examples of applications, if we consider uniform initial temperature, the same temperature in all parts of the system in the beginning, then we can just sum this squares of Bessel functions, and there exists a known identity that is just a Bessel function of zero order and of the double argument. And this gives us the oscillations of kinetic and potential energy, which finally give us the equipartition is this energy, which is really very picturesque process. And also we can, this is so-called fast process because it's comparable with the time of oscillations of each particle. And after this fast process stops, then we can speak about the slow process, which is, of course, of maybe of more interest, the process of heat transfer in the lattice. Now, what about the slow processes? They can be described by many ways. One of the attractive ways is to describe it using kinetic approach based on the Boltzmann equation. And this is actually not straightforward, because from one hand point we know very well from physics, from elsewhere, that wave processes and processes of particle motions are very close to each other. But anyway, the exact how we can transfer from wave equations to the equations describing motion of particles, it's not up to my mind very clear up to now. Anyway, what can we do? We can write, we can suppose that the energy, heat energy, is transferred in the crystal by small portions, which are like kind of particles. They usually are associated by phonons, but it's a question if we can speak like about this like phonons, because this should be something localized. Anyway, consider we can some localized portions of heat energy which travel without interaction, because we have harmonic lattice. Then we suppose that we introduce the probability density function, that this particle appears somewhere in the certain place of the system, in this certain range of velocities. Then we write Boltzmann equation. We postulate that temperature is proportional to integral over velocities. And then it can be easily obtained that if we have some initial velocity distribution, we can obtain these two formulas for kinetic temperature, which actually can be obtained by other ways, by solving using DFT transform or any other ways. And after some approximations, continuizations, a lot of work, we will obtain the same equations. So this technique is close to this technique is used for many systems, for nonlinear systems, but up to my mind is still not very well understood what actually are these particles and how they connect to the wave phenomena which we obtain in the system. And this is an important question. So here you can see the evolution of the heat pulse in the which is described by this equation. So we have for this harmonic system the wave behavior, which is quite different from the diffusive behavior which we know from macroscopic experiments. Another very interesting a very interesting behavior is connected with the decay of sinusoidal temperature perturbation, which actually also can be described by this equation. But what is important that we have, this can be described by this reversible equation, which actually is very close to Bessel equation, but only we have additional derivative, space derivatives. But reversible equation give irreversible behavior. This is also a challenging question. Another big challenge is connecting what is happening with the entropy in this system. We have situations with during this behavior that heat goes from cold to hot. It has inertia. Asymptotics of the thermal wave is another interesting thing, that because it's after some time it became some special shape, and it can be obtained in the more or less simple formulas. There exist the situations when we have finite crystal, we can observe phenomena like thermal echo, which is temperature can go down and then rise again, which is also very interesting, and we don't actually know what is happening after a lot of these echoes go one after another. Decay of the continuum solution, which actually, if we consider this kinetic approach, we should keep in mind that after some time the packages they go wider and they became they can't be treated as point of some localized phenomena, and in this case this kinetic solution is not valid, so it has some kind of time of lifetime. And what is happening with this solution you can see here on this picture, and the lecture will be given by Andrei Murachov today later about how this decay can be observed. Time scale, actually, what is important, I think we have heard an excellent lecture by Antonio Politi, where we can see that at different time scales, different behavior, system can demonstrate different behavior. I mean, these discrete systems. And here we can see that at different time scales and different length scales, we have also different phenomena in this simplest model of Hooke's chain. So for for short times, we have this fast behavior, local equilibration, that slower processes are heat transfer, even more slower, the asymptotics, the thermal echo, and at the high times we have decay of continuum solutions, and at the end we can go to the recurrence, which is probably need extremely large time, and nobody knows if it can be obtained in reality. So there are several questions which are up to my mind don't have the complete answers. So the quasi-continuum representation, as I said, and today I think the next lecture, not the next, but yes, the next lecture will be done by Professor Gavrilov, and a very interesting representation of the discrete systems, this and with localizations and so on. The nature of quasi-particles and kinetic description. Also, this is the question which we have some answers, but I'm not sure that they are complete. Time scales, this is challenging. What is happening in long time asymptotics is also unknown, and also even how to state the initial conditions for non-steady heat transfer processes also not very well understand it. And of course, everything which happens with entropy definition and entropy behavior for non-steady processes, also there are many questions. So I think that's all what I wanted to say. So thank you very much for your attention.
Okay, thank you very much, Professor Krivtsov. So I think we have time for one very short question, because we are again running out of time.
Can I ask?
Yes, please, Dmitry Anatolyevich.
It's of course, Anton, it's a very wonderful report, and it's very important for me because this report includes all problems and some results of your team, common team. And of course, it's very interesting, and thank you very much. I share a little question, but it's the question for me, it's so common question for this problem. Let's see at the page when you show the Boltzmann presentation of the formula for integral of temperature. It's the traveling wave with the constant velocity v. Your presentation when you show the integral of temperature with group velocity. What two?
Yes, yes.
You understand me? Yes.
This one.
No. Your discussion, your page about the Boltzmann and your presentation when you show that the temperature traveling with the group velocity. Oh, here. Let's see the last two formulas. The last, what here and here. Yes. So as we know, any function can so present can they find have the kind of so integral for the spectrum as you see this is the last formula. Boltzmann think and thought about non-dispersion. You showed the formula with dispersion. You can take the group velocity. You take the group velocity from the curve which you find from the usual equation from our classical equation.
Yes.
How do you think? It's maybe some, how to say, problem. You take the group velocity from the equation which we took from the long wave approximation. Then you take this, go to the here formula and try to find the, of course, you know, usual any perturbation in system kind of traveling with group velocity, any, and temperature and displacement and stresses and strains, any. The main question, the main energy of the perturbation, how to find this. And the diffusion problem is showed that the main energy with diffusion and a little energy with the high group velocity. How do you think with this? For me, it's problem. I shall take the group velocity from the classical equation, but I shall think about your formula for high, it's stochastic and etc. What? How do you think? It's
Yes.
correct. It's correct, and it's not.
Thank you very much, Dmitry Anatolyevich. I think you're absolutely correct. So actually the amazing thing is that when we use this, for example, Boltzmann representation, and we are just saying that there are some kind of portions of energy which travel somehow, we don't know how they travel. We just assume that this is kind of law. Then we obtain the formula, which is the last one here. And it appears to be exactly the same formula which we obtained by absolutely different way, by using the, true, very long solution of the system of linear equations, which are actually the description of this system. And again, this function which we appear, if we compare, we see that this is really the group velocity dependence of the wave vector. So, and here these two absolutely different theories connect, which is, up to my mind, extremely interesting. But again, it's, I can't say that I understand completely the mechanism which works here.